a new section, 4.3. We are going to look at how derivatives help us to understand the shapes of graphs. So I'm going to begin by giving you a kind of rundown on the basic names that we give to the shapes. So let's talk about increasing and decreasing. So here's my function. The color codes will be clearer in a minute. Going up and down, up and down. A function is increasing if from left to right you're going uphill. So increasing in here. Now in this particular picture, starting at an x coordinate of -5 all the way up to this x coordinate of -2, this function is increasing. Starting at 2 and finishing at 7, it's increasing. These are not coordinates, these are intervals. This is from x is 2 to x is 7. This is from x is -5 to -2. And would you agree there's another place from 11 to 17? And in these intervals, this function is going uphill, it's increasing. Can you imagine, you know, derivatives, right, increasing. Normally we would put little union symbols, and that's what you would do in 141, remember? Increasing, going uphill, decreasing. Well, how about the green ones? It's decreasing from -2 to 2, and it's decreasing from 7 to 11. Are we comfortable about if I gave you a function y equals f of x, and I said, look at this picture, tell me where it's increasing and tell me where it's decreasing? Do you feel it's pretty obvious what it is? Why are these brackets curved and not the square ones? You know, the brackets that look like that.
Because you're not including that point?
That's exactly why. You're not including that point. Now you might say, well, why am I not including? Let's take an example, 11. Isn't 11 a decrease, but it's also the beginning of an increase? And you're not allowed to be both. So you can't be any of them. So you don't use them. So here's a good rule that typically, do you notice all the intervals are open intervals? That just means you don't include the boundaries. Now, this is not mathematics, this is WebAssign. WebAssign doesn't, it seem like the little union symbols. So when you're doing your answer in WebAssign, you give an interval, comma, the next interval, comma, the next interval. And I wish you didn't have to do that, because, you know, that's the way you should really write it in math. But you got to do what you got to do.
I think in one of their symbols menus, they have a specific one for it. I think I've used it like one time.
Try it. If it takes it, I'll say thank you, right? It might, I know it takes commas, but if it takes a union symbol, that's just better math. So if you can make it happen, you can do that. I hope that's true. It would be nice if it had that symbol. Oh, while we're at it, what do we call this funny little corner thing that starts with a C?
The cusp.
Yeah, it's called a cusp. Just thought I'd put that in there because it's there. Now, see at this point here, and at this point here, and yeah, that point there, and finally at that point there, don't we have local max and local mins happening? So at this point here, isn't this a local max? So at x equals -2, there's a local max. At x equals 2, the local min. At 7, there's a local max. Even though it's a cusp, it's still a local max. And over here, there's a local min, right? So isn't it typically when an increase changes or transitions to a decrease that you get a local max? And when an increase turns into a decrease, when there's some kind of changeover, isn't that very often where you get local max and local mins living? So far, so good. So that's what increasing and decreasing and local max and mins look like. Let's look at a new thing Well, I don't know how new it is, but it is new probably for most of you, and it's called concavity. There are two kinds of concavity. A curve is described as being concave up when it looks like a happy face, and it's described as being concave down. So any point on that is called concave up, and it's concave down when it's like that. But concave up doesn't need to be, the entire thing doesn't need to be a happy face. It can just be part of the happy face and it's still concave up. And it can be just part of the sad face and it's still concave down. So to be concave up or concave down, you only need to be in a happy face or any sad face. Even if it's only the left side of a sad face, it still counts as being concave down. So let's look at this fella. Would you agree that in this region here, the one I'm kind of making red, would you agree that this part of the shape here is concave up? Isn't it a happy face? Would you agree that at this region here, the stuff that's kind of green now, would you agree that this is concave down? Now we have a little bit of a problem here because we want an interval of concave up. Well, I know I can start at -3, right? But isn't there going to be a transition between the happy face and the sad face? Won't they eventually meet up at some value? And I'm going to make it 4. So there is some place where a happy face transitions into a sad face. So in this question, it's going to be -3 to, I've decided that's a transition point to 4. And then it's going to be concave down. For values of x between 4 and 8. So if you see a happy face meeting up with a sad face, don't you have to kind of make a judgment call about where that change happens? Now I picked 4. Some of you might have picked 3, and I wouldn't argue about it because there's a bit of a grey area. Would you agree? So somewhere 3 or 4 depends on what your visual, how you look at the thing is. You don't expect accuracy in the transition point. So you might even say 3.5 or 3.6 or 3.3. For the sake of making your life easy and WebAssign as well, will you pick whole numbers for the transition point? So it's either 3 or it's 4. Go with 1, and if WebAssign says no, go for 3, right? And if 3 doesn't work, go for 4. It's probably not going to go 3.1234 because nobody could ever make that judgment call based on just this function. So are we happy about concave up and concave down? A curve is concave up if it's part of a happy face. A curve is described as concave down if it's part of a sad face. And there's a third and final term, and it's called a point of inflection. And a point of inflection is actually a coordinate. And this is one of the problems with interval notation. This is an interval. It is not a coordinate. It's all the values of x from -3 to 4. You're part of a concave up curve. These are all the values of x from 4 to 8. You're part of a concave down curve. A point of inflection is a single coordinate 4, 3. Don't they look exactly the same? So it's all about context. If it's a point of inflection, you are looking at a coordinate. If it's a concave up or concave down, you are looking at an interval, right? So you just have to know when you are looking at something, whether it's an interval value or whether it's a coordinate value. Are we okay with that? The notation, I guess we just didn't have enough different shaped curves, right, to do in our parenthesis. So that's what happened. Right, let's show you what this looks like. It's homework. So I'm going to show you a curve, hopefully. Are you looking at a graph now? Question 1. You're not. Are you looking at it now? Okay. Here is a graph of a function. Give me an interval of x's where this function is increasing.
1 to 3.
Give me another one where it's increasing.
4 to
4 to
6.
6.
Give me an interval where it's decreasing.
0 to 1.
And another one.
3 to 4.
Would you agree that increasing and decreasing are pretty easy to do if the graph's in front of you? Okay. Now, happy face. Give me an interval where this shape is concave up.
0 to 2.
Agreed. Would you agree 2 is probably the transition between the happy and the sad face? So 0 to 2. Agreed? Right. Concave down.
2 to 4.
Agreed. Now, not so obvious. Another concave down.
4 to 6.
46. Now, you got to use a bit of imagination here. Isn't 46 a bit of a frown? It's like the left-hand side of a frown. Can you imagine it curving round eventually, maybe? But you got to be concave up or you got to be concave down, right? You have to, a curve has to be one or the other, with the one exception of a straight line. A straight line has no curvature, right? Because it's straight, right? But if you're curved, you got a curvature, right? You're either concave up or you're concave down. If you're a straight line, you don't have any curvature. So that's the only exception to the rule that you must be. Right, try another one of those guys. Okay. Give me an increasing interval.
0 to 1.
Give me another increasing interval.
3 to, wait. 3 to
Ah.
5.
Yes. And then 5 to whatever, 7, right? Bit sneaky, that one. What's the problem with 5? You know, x equals 5. Why isn't it part of an increase?
It's kind of just flat.
Yeah, and flat means zero derivative. Flat also means you're not increasing and also means you're not decreasing. So you don't use me. So you're going to have a 3 to 5 interval and a separate 5 to 7 interval. I'm assuming this function starts at 0 and finishes at 7. Okay, give me a concave down.
1 to 2.
I want more
Sorry,
than that.
0 to 2 is what I-
Agreed. Give me a concave up.
Did you say 2 to 4?
I would. Yeah, I would say 2 to 4 is a concave up. Give me a little baby concave down.
4 to 5.
4 to 5.
45. Give me another concave up.
5 to 7.
Right, do you see as you travel along that curve, aren't you part of a happy face or part of a sad face, right? You got to be one or the other. There's no straight lines in this shape, right? You got to be one or the other. Now, give me the coordinate of a point of inflection.
4 3.
2 2, 4 2, 4 3. 2 2 is one of them. Would you agree at 2 2? There's a happy face and sad face meeting up. What's happening at 4 2 is on the left you've got a happy face, and the right you get a sad. So 4 3 is the coordinates of a point of inflection. There's one more point of inflection hidden in this shape.
5 4.
Yeah, at 5 4. On one side, don't you have a concave down? On the other side, you have a concave up. A point of inflection is the transition, right? It's a coordinate of a place where there's a transition between a concave down turning into a concave up. That's what a point of inflection is, right? A happy face shape is turning into a sad face shape. At that place, we call that a point of inflection. Okay, let's hide that for a minute. Return back here. So if I gave you a sketch of a function, you know, one of these kind of guys, would you feel comfortable about telling me where the intervals of increasing, decreasing, concave ups, concave downs, and finally points of inflections? Okay. So let's, move on. Let's look at now. Here we go. How to use derivatives to find increasing and decreasing. Okay. Well, here is how we're going to do that. A function, y equals f of x, is increasing when its derivative is positive. When it's decreasing, when it's, I guess I'll put the word in when its derivative is negative. Well, let's see how that works. Still got my picture handy somewhere. Yeah, now this guy here. If you take any of the places where the function is increasing, won't its derivative be a positive slope? That makes
It froze. I can't hear.
it still frozen? Can you hear me?
Correct.
Hey, now, yep.
Is my finger moving? It's not frozen anymore. Phew, okay. So we
It's
can
very
use
delayed, but it's getting there.
It's a bit of a slideshow.
Your webcam's good, but the other one isn't very great.
well, this guy here. This fella here is not being it's not being good. Oh dear. I'm just hoping spontaneously it starts working. Is it is still bad? Still bad. Well,
Someone
that's
recommends trying to turn down the webcam quality.
I don't know where that feature is, and the chances are if I went looking for it, I would probably make it go off and I'd never find it again for a wait. Let me see if I've got anything in here. It might be a feature unconnected with that. Let me see if my virus checker is running in the background. So I'll be back in a second, guys. I'll stop sharing. I'll go back in. I'll start sharing. Maybe that'll do it. Is it still slow? Is it choppy?
It's still
or...
loading.
Yes.
Oh God. Okay. Then I'm going to stop share. I'm going to go up here. I'm going to exit full screen and see what's going on in the background. Now I've got that. That shouldn't cause any trouble. That's not causing any trouble. It's just meetings. That's not causing any trouble. Is my virus checker on? Yeah, that's not a problem. I've got an update, that's nothing. Well, my wife's not here, so it's not that she's sucking off any bandwidth. I can't see anything. Okay, guys, I am going to go away. I'm going to switch my computer off and switch my computer on. And you lot are just going to hang about, and hopefully it only takes a few minutes. That's all I can really do right now. Okay. We'll just give a few minutes for everybody to get back into the room. Right. We're going to have positive thoughts here, right? I want nothing but positive vibes. Okay? If I even see one look at a negative vibe, you are in trouble. So look, Matthew, I don't know what kind of face that is, but it's kind of scary. You shouldn't do that in public. I want to frighten the children. Okay, Andrew, looks like the last one coming in. Right, I think that's everyone. Okay, moment of truth. Is it normal speed? I get one shaking head, that's not good.
It's better, but
Yeah,
it's
a
good
little
enough.
better.
It's good enough to keep going, okay. I'll just keep going. I'll try and talk through it. I hope you can hear me better than you can see me. I'm not doing it right now because it takes too much time, but once this lesson is finished, I'm going to just reboot my modem. I'll just switch everything off and maybe it just needs rebooted. Okay, so let's look at how to find increasing and decreasing from a function. This is our example. So what you do is you find its derivative. And then you factor the heck out of it. So I'm going to pull out 9 as a common factor. And then I'm going to recognize, hopefully you will as well, the difference of 2 squares. So imagine the question was, find the intervals of increasing and decreasing for this function. So far so good. Now, you find the critical numbers. In this case, and pretty much most of the cases, it's going to be when the derivative is 0. And since I've already done all the hard work with the style points, would you agree it's pretty easy to find the 2 x coordinates where this derivative would be 0? Because what's going to happen is that that's going to be the transition point between an increase turning into a decrease or vice versa. So what I then do, once I've got the critical numbers, is that, and there are different ways to do this. I've seen other people do tables of values, and nothing wrong with tables of values as well. But I, kind of visual person, I like number lines. And this number line is going to be the value of the derivative. Now, what do I know? Well, I know at x equals -2, the derivative is 0. And I know that x is +2, the derivative is 0. What that has essentially done now, imagine these are little invisible walls, is that the number line has now been broken into 3 regions. Values of x less than -2, values of x between -2 and 2, and finally values of x greater than 2. And inside each of these regions, the function will only be increasing or decreasing. It won't be sometimes one and then the other, and the argument's going to be something like this. Let's just say, for argument's sake, that it's positive in here, right? Well, if it was positive, it can't be then later on negative in this interval, because we're talking about functions that are continuous and differentiable, right? Not weird ones that jump all over the place, right? Smooth curves. And for smooth curves, you can't go from a positive to a negative, right? From an increase to a decrease without passing through zero. Does that make sense? So what you then do is you find what are called test points. So what's that is just pick one point to represent the whole region. So in this case here, I'm going to do a test point in -3. What do you think my test point might be for this middle region? What value of x would be a good one to choose, do you think?
0.
I would. And over here, my third one, you'd pick 3. But technically, it doesn't need to be 0. Couldn't 1 and -1 do? And if I just felt weird, couldn't 1.23456 do if I really wanted it? Now, for each one of these test points, we find the value of the derivative. Well, the derivative is this guy, right? So it's 9 lots of -3 add 2 times -3 take away 2. That's -5. What's that? -5. -1. So that's 5. That's 45. But I don't really care so much about the 45 part. I really just care that it's positive. And because it's positive there, that makes it positive everywhere. So I can now tell you that this function is increasing for values of x forever up to an x coordinate of -2. So any value of x in that region has to be positive. It has to be increasing. And then you do x equals 0, and you find the derivative at 0. And that's 9 times nothing add 2, nothing take away 2, and that ends up being what, -18, which is definitely negative. So in this region, oops, everybody is negative. And we know negative means decreasing. So values of x between -2 and 2 are decreasing. And at x equals 3, let me show you a little trick that I use. I don't really care about the number part. I don't care that it's 45 or 4,500. I only care that it's positive. So what I do is, if I want to find the value at 3, I just say, okay, 9 is positive. 3 take away 2 is positive. 3 take away, add 2 is positive. 3 positive numbers, my answer is positive. So it means I don't need to do heavy duty multiplication. Don't I just need to say that guy's positive times that guy's positive times that guy's negative, or whatever the combination is. And from that, I should be able to tell the final answer is positive or negative. And which means that this fella is also increasing. So the first derivative of this function, which is this guy here, has generated this number line. And from this number line, I can now tell you when it's increasing, when it's decreasing. I can do more than that. Let's look at this guy here. See the plus to the minus from increasing to decreasing, right? When the derivative is positive, doesn't that mean it's going uphill, right? When the derivative is 0, it's flat. And when the derivative is negative, it means it's going downhill. Isn't that a local maximum then at x equals -2? Do you see I've found a local maximum just for free, right? I didn't need to do extra. Right, what's going to happen over at x equals +2? Well, on this side, it's a negative derivative, so it's sloping down. 0 derivative is kind of flat, right? Positive derivative's up. Hey, haven't I now just found a local minimum? So if you have a function and you turn it into its derivative, this derivative, if you factor it well, will allow you to find all the things about increasing, decreasing, and as an extra bonus, you can even find out where local max and mins are. That's pretty impressive, right? Great, pretty cool. Let's look at second derivative. Right, so I'll write my original function down. Right, there's one second derivative now. If the first derivative tells you about increasing and decreasing, what do you think the second derivative might be telling you about the original curve?
Concavity.
It is. And here is the property. If the second derivative is greater than 0, that's positive. The function is concave up. If the second derivative is less than 0, right, negative, then it's concave down. Right, I've got my second derivative. It's not the most difficult second derivative in the world. Would you agree that it's equal to 0 when x equals 0? Right, 18x is 0 when x is 0. I draw a number line, just like I did before, a much smaller number line. And this number line is going to contain information about the second derivative. Well, I know that at x equals 0, the second derivative is 0. And I do test points. This time I only have 2 regions to worry about, right? Everything to the left is 0 and a different one, everything to the right. So how about a test point of -1 and then later on a test point of +1? Now at the test point in -1, the second derivative is -18, so it's definitely negative. So everybody is. And at x equals 1, the second derivative at 1 is positive. So everybody is positive. So I should be able to just tell you when the intervals, when it's increasing and when it's concave up and when it's concave down. Well, it's going to be concave up here. Because when the second derivative is positive, it's concave up. And it's going to be concave down when the second derivative is negative. And for free, I can find a point of inflection. A point of inflection is where a concave up changes into a concave down or vice versa. Would you agree in this case it's at x equals 0? Now I can't give you the coordinates because nobody, well I could now I guess, I could go up here and tell you what it is because the original function is here. So it would be at 0, 0, wouldn't it? So if I give you a function f of x, if you use its first derivative, can't you tell me all the places it's going to increase and decrease? If you then find the second derivative, can't you tell me the intervals where it's going to be concave up, concave down, and point of inflection? Very good. So for what we've got left, let's look at what the graph of the derivative function tells us. What does it tell us about the original function? So imagine I don't tell you what the original function is, but I found its derivative and I put it into Desmos. And Desmos came up with this. So that's -3, -2, -1, 1, 2, 3, 4, 5, 6, 7, 8. There, I think I've got most of the points there. This is a sketch of the derivative function. This function tells me pretty much everything I need to know. Let's talk about when a function is increasing now. Intervals where it's increasing. What does the derivative have to be, or what will the derivative be when it's increasing? Positive or negative? The first derivative, is it positive or negative when it's increasing?
Positive.
Positive. Now, won't that be from here to here? Isn't the derivative positive? Positive is above the x-axis, right? So I know it's increasing here. Would you agree that it's also positive derivative in this region? So that makes it increasing here as well. So it's increasing from -1 to 2, and then from 6 to 8. Now, won't this function be decreasing when its derivative is negative? And a derivative is negative when it's below the x-axis. So that makes it decreasing here, and it makes it decreasing here. And from here to here, that's values of x from -3 to -1, and from 2 to 6. Are you happy about how you can use the sketch of the derivative to find increasing and decreasing? So you got to think differently now. This is not the original function we're looking at, right? This is the derivative function. So it's telling us things in a different way. Can you see it's increasing when it's got positive values, and it's decreasing when the derivative is negative values? So it's a little bit different. Now, these three guys here, I know, make them over big. Aren't they the three places where the derivative is 0? Well, let's look at one of them in particular. Let's just focus on at -1, right? If you see what it looks like at -1, it looks something like that, doesn't it? Right, if you just focus there. Now, on this side, isn't the derivative negative, and on this side, it's positive. And right in the middle, the derivative is 0. So what we're looking at here, we're looking at a negative, a 0, and a positive. Can you see that's a local min at that point? Right, what's happening at this one? Well, it's positive, 0, and negative, right? Positive, 0, and negative, that's a local max. What's happening here? Negative, 0, positive. Negative, 0, positive. Isn't that another local min? Do you see I can see the local max and the local mins here? So doesn't this not just tell me increasing and decreasing? If I look harder, especially at the x-intercepts, can I also tell where the local max and mins are? And whether it is a local max or a min, right? I can look at this and say, Oh yeah, I can see that's negative derivative. So it's pointing down the way, then it flattens off and then it points up the way. Well, a down the way, flatten and up the way is what a local min looks like. So far, so good. Now, for the few oops, not everybody made it. For the few moments that we've got left, I am going to show you what that question looks like, hopefully. Are you looking at question 3? Okay. Was it usable, the thing, or was it kind of jittery, the written stuff? Could you use it at least?
It was
Yeah.
okay, yeah.
Okay, no, it's not bad. Right, so let's, well, darn this thing, go away. Go over here, that's better. In case I forget, will you remember to say hi while this last question's been done? Right. Okay, here is question 3. This is a derivative function. So you're going to answer the same kind of questions I did a few moments ago. Give me an interval of x's where this function, the original function, would be increasing.
2 to 4?
No, you are looking at that as if this is a sketch of the original function. This is a derivative function.
Right.
So when is it increasing? That's when it's positive, right?
Yeah.
Positive numbers.
3 to 5.
3 to 5, right? This is a derivative function, right? So you have a cap on when it's original and a different cap when you're looking at a derivative. Where else is it increasing?
0 to 1.
Okay, when's it decreasing?
The 3.
1 to 3. And the other place where it's decreasing?
5 to 6.
Right. Doesn't that tell you everything you need to know about increasing and decreasing? Right, the original function. Right, there's a critical number at x equals 1, another at 3, and a third one at 5. We agree the derivative is 0. Focus on x equals 1 for a minute. Would that be a local max or a local min in the original function?
Local max.
It's positive 0, negative, local max, agreed. What would be happening at x equals 3?
Minimum.
Yeah, local minimum. We're going to do this tomorrow, but we broke up with time, but just I want to make you think about it for a minute. If first derivatives tell me increasing, decreasing, local max and mins, right, if that's what they can use for, what do you think the second derivative is going to get used for? So a sketch of the second derivative function.
Going to tell you the increasing and decreasing of the first derivative.
Which is called concave up and concave down. So the second derivative graph will tell me when a thing is concave up, when a thing is concave down, and the pointers of inflection. So first derivative graphs tell you increasing, decreasing, local max and min. Second derivative graphs tell you concave up and concave down of the original function. Okay, thanks for hanging in there. Overshot the time a little bit, but hopefully not too much. You've already said hi, I hope, and bye-bye.